Okay, so concavity, which is nothing but a description, informal description of the graph that you see when you can say something specific about the sign of the second derivative. So the sign of the second derivative gives you the change of the first derivative. In other words, the rotation of the slopes. So this is an example of how simple it could be. If at the simplest, this is what it's about. The rotation of the tangent, like this, right? So the original was like this, and then it became that. So it rotated clockwise, and it means that the second derivative was negative. It means that it is declined. So f prime here, f prime is decreasing. Okay. So once again, the starting with a pink slope, and then if you compare it to the next one, it has rotated clockwise, and clockwise means that the slope has decreased. Okay, and slope decreased, that's f prime. Okay, on the other hand here, f prime is increasing. So similarly, if I continue this way in order to compare, this is my rotation of the tangent line, and it is counterclockwise, which means that the slope has increased. And that idea remains even if we proceed to the function itself is decreasing or increasing. It doesn't make any difference whatsoever. Okay, so once again, you observe here rotation clockwise, and here you observe the rotation counterclockwise. Okay, so once again, I continue the line from the beginning, from the first kind of time interval, and to the next, and so that I can compare them. And another way to see it is think about sitting in a driving a car and seeing how things are passing through your field of view, whether left or right. Okay, so and from that you can conclude which way your rotation is happening. A rotation of your car relative to what's going on, and relative to the environment, and then conclude something about the curvature, which is once again a topic from Calculus 3, but certainly, where is that? I had that picture here somewhere. Here it is. How the curvature might be higher or lower depending on the magnitude of the second derivative. The sign, however, is the most right now. We don't really care much about the shape of the graph. So more curved, less curved. It is more about just to say whether we're turning left or right. We're always driving left to right like this, okay, and because that's the x direction of the x-axis, okay, and then we're looking at what's happening to the tangent lines. They decrease or they increase. Okay, so that is the idea, and if you get the second derivative, find its sign as we did, then you can't tell what the graph is going to look like. So this is a very short example of that exact situation right here. So 10x, the derivative negative 10x squared, the second derivative 2x cubed. And then it becomes interesting when you want to sketch the plot of the graph when you have both. Okay, not only the graph looks like like this over there. It's in purple over here. As you can see, it's going kind of a down, but at the same time it could be wiggling. Okay, so that is not a pretty picture. But if you have the second derivative, you can eliminate the possibilities of wiggling, which is nothing but changing of concavity. So you can see how if you go along the purple line, it turns it first concave down, then up, down, up, down, up. Okay, so if that's not the case, as we have discovered right here, the second derivative, as you can see, it is all negative and then becomes all positive. So two intervals, and on which the derivative, each of which does not change the derivative. So within each of the intervals, you have one branch in each. And those branches are not only, we know how they increase, that's from the first derivative, but we also know the concavity. And that's the final product is here. Very, very nice picture. Decreasing, to be sure, you probably will need also, to complete the picture as is, we would need also the asymptotes. We do it one at a time, topic one at a time. So we want to understand functions, how they behave, and how we can discover these behaviors from pretty much algebra. Okay, so given a function, we want to understand how it behaves based on algebra. It's either early on there were limits at infinity or infinite limits, and those would give us asymptotes, vertical and horizontal. Now we're using first derivative, second derivative, and once again that gives me a good idea about what the shape looks like. But right now we just push asymptotes aside, even though they're certainly important. You cannot conclude necessarily that the graph looks like what's on the right. Best you can do is this. So just decreasing concave down, decreasing concave up. That's all we know. Okay. However, it is an important topic, and this is what I wanna give you an example of what can happen. The formulas, you often start with the formulas, but it's not really necessarily the case. You can have the graph of a function, just the graph, and no formula. Okay, so and then you at least should be able to look at the graph and describe its behavior. Indicate all the concavities, as well as increasing, decreasing behavior. So always every problem we solve, there is the inverse of that problem, and so we have to do it. So suppose I randomly drew a picture, and now you're supposed to, the problem would be is to subdivide the domain into intervals and indicate what kind of behavior is there. Okay, and so the problem might be stated very loosely if we're talking about some kind of test. So because you already know, you're supposed to know what questions to ask before you answer them. So you look at the picture, you're supposed to describe. Number one, you certainly know what we're talking about, and that's increasing, decreasing behavior. So where does that change? Usually it is at the the maximum points. That's where the behavior changes, and then like this. So that's my first interval. But then there are this point. Well, actually, that's not the point. As a matter of fact, as you can see, that's a questionable. Let me just point it out that there is no change in the increasing behavior. To the left as well as to the right of the function of that point, the function is increasing. Okay, so even though it is a point, a suspect of some kind of behavior, turns out that as far as the monotonist is concerned, there is no change there. But there is something else changes. What changes at that point? Well, there is always, the slope is constantly changing, but what's so special about that point? Well, let me see.
It doesn't go to negative.
What?
It stays
The slope is zero.
The slope is zero, yes. Let me draw a picture. So we're going backwards, and I have right now 4 intervals on my domain, 1, 2, 3, 4, and I can mark, just looking at the picture, I can say, well, this is increasing, decreasing, increasing, still increasing, right? Okay, so I certainly, it does make sense to point out that, well, I put 0 here to remind myself that their slope is equal to 0. Okay, that's helpful. I could, slope equal to 0, what does it mean? It means that the derivative is equal to 0. So f was, this is y equal f of x, and its behavior is recorded here. Now, I want to say something about the first derivative. Okay, so what do I say about the first derivative on these intervals? Positive, negative, positive, positive, and 0 in the middle. All of these are zeros. The slope 0 means the derivative is equal to 0. Okay, to begin with, the next, then we don't stop anymore. We proceed to the second derivative. Well, actually, probably it is a good idea to actually think about the second derivative secondly if we are doing the first derivative. We know what's happening to the second derivative, so I'm going to be looking at the slopes. So these are the slopes. The answer about the sign of the derivative has been answered right there, but now it is a finer analysis. What is happening to the slope? It's suppose it's positive, but what else is happening? What else is happening? What point should we pick? What points should we pick on the next level of analysis? monotonicity, and the next level analysis is concavity. Okay, so then we'll look at points where the concavity changes. Can you point them out?
Is it all the zeros?
No, that's where the monotonicity changes. And let me give you a hint right away. The second, knowing anything about the first derivative like this does not tell you anything about the second derivative and vice versa. So you have to just ignore that orange stuff and just start from scratch and pretty much look at these slopes. Where does the monotonicity? Where does the concavity changes?
Wouldn't it be from the first to the second and the second to the third point it changes? Where it goes from positive to
Yeah,
negative?
it does. It has changed, but there is an exact point where that happens.
Is it the zeros on the graph?
No. I mean, if you're talking about this point over here, then it kind of looks like it, but actually, it's not exactly there. And if it is, it's only by accident. The point, I think, is here somewhere.
Oh, it's in
Where it crosses the x-axis?
What?
Is it where it crosses the x-axis?
No, you see, it is. If it does, it's only by coincidence. If anything, let me make that point clearer by copying this. We're done with this stage. Okay. Copy. Where's the copy? Paste. Okay. So I'm taking the same graph. I'm locating it in the exact same spot, if I'm not mistaken. Yeah. Okay. So it's the same spot, same function. I'm going to erase what is irrelevant now. Erasing meaning erasing the what we just did with the first derivative. So this is all irrelevant. That special point over there, it's not important. Okay, so ignore everything else. You can even slide out of view. Okay. I don't think I can kill this one. Nope. All right. Okay. So where is the slope changes? Where does the concavity changes? So remember, up, down. Okay. So this is the point somewhere there where the concavity changes. Concave down to the left, concave up to the right. Okay. Do you see more points like this?
The exact opposite.
Yeah, here somewhere. I think it's reasonable to say it's here. That it?
No, there's another one.
There's
About
another.
halfway.
Yeah, it's where it's kind of flat in this area. Okay, so these are the important points about that where the concavity changes. So let me write that out. So I'll have so on this x-axis, I will say something about the function, which is concave down, concave up, concave down, concave up. So once again, this is just an indication of the behavior. I don't want to write so words for whatever reason. I'll just put it in the form of those little wiggles. Okay. So once again, these are the separators. Okay, and then furthermore, this is what happens to. This is how we would describe the function itself, concavity of the function. But if we were to proceed to the second derivative, well, if we proceed to the first derivative, what's happening? Look at the first wiggle. What's happening to the first derivative?
It's decreasing.
It is decreasing. Yes. Look at the slopes like this. And then it is increasing, decreasing again, increasing. Okay, so that's what we have discovered. And then, just for completeness sake, so I'm asking the same question about the second derivative. What does this tell us about the second derivative? So the first derivative is decreasing. What does it tell us about the second? The second derivative is the derivative of the derivative.
Is it increasing or decreasing
No.
too?
It's negative.
Yeah.
It's just negative. Okay, negative, positive, negative, positive. Okay, so as you can see, this analysis is happening independently of analysis of the sign of f prime. Okay, but then if you want to really, as you can see, there is a. Do you see the any relations between these? These special points, two kinds of special points marked on the same graph. So do you see them going from left to right? As you can see, well, let's just go left to right, and I'm going to have a maximum point. Well, let me first say that these are called the inflection points. Okay, that's where the concavity changes. So if we move from left to right, then we have a maximum point, inflection point, minimum point, inflection point, and then the last one is interesting because it is actually the same point. It's the same point where the derivative is equal to 0, yet nothing is happening, sort of, because it continues to increase, right? But the concavity does change, so that can happen. Some even though it's not as dramatic as the change of monotonicity from increasing to decreasing or vice versa, but the concavity has changed. So that is also something. So then the answer would be, if either how would you describe it? I just didn't use words, but pretty much if I the answer usually is written in words rather than in diagrams. So if you want to describe this in mathematical terms, this function, what would you say? You say that you just rewrite what you got there. So f increasing on, and now list intervals. Let me mark these somehow. Say, well, let's put some numbers here. So say this is 1. This is, say, 4, and this is 5, 10, I don't know, 13, and the last point, say 20. Doesn't matter really. 20. Okay, so this is how we describe it. Then f is increasing on the interval. So there are four events to be described, or rather patterns to be described: increasing, decreasing, and concave up, concave down. And then at the end, a maximum minimum points. That would be a complete description. So f is increasing on the two intervals wherever you see the arrow is going up. So I see it's on negative infinity 1. Okay, then it is increasing on 10 to infinity. That's it. Okay, so that's the increasing behavior. Then f is decreasing on what's left, which means 1, 10, yeah, and that's it. Okay, so one interval of decreasing behavior. Then, so that's the first stage. The second stage, I'm talking about the concavity. So f is concave down on negative infinity 4, and then 1320, and f concave up. What's left is 413. And 20 plus infinity. Okay, and then as I said, then it is probably often the most important thing to conclude, and it is to specify the maximum minimum points. So max at local of course. We can only speak of local ones. At maximum at 1 and minimum at 10. So that would be the complete description of the function. Okay, so as you can see, once again, there is no derivative, and it is online if you most of the time, and you get the formula, and then you're supposed to arrive to a picture through investigation of the formula of the first derivative and the formula of the second derivative, just as we did over here, right? So we computed the actual formulas for the derivative, second derivative, and that's how we were able to discover all we needed to discover. about it. But it is also possible to go vice versa because you never know what kind of problem you're gonna face. Okay, so the formulas, so the differentiation then becomes more important because it is where you this is a tool of studying functions. So as a means to an end is to come up with a picture like that. So sometimes the picture is more complicated than this, and then factoring of the first derivative, second derivative, that's something that you need to do. Let's see, did I do enough of these? So this is 1 on x, concavity, the exponential, yeah, let's do the exponential function. Not this one. Yeah, okay, no, we did one. Let's take another look at it. So a slightly more complicated function, and once again, we derive the information from the formula or formulas to end up with a picture. So formulas, algebra gives you a picture at the end, or you have pictures, and then you're supposed to say something about those functions, even though there are no formulas. Okay, but it is fairly straightforward. Once again, it's always the sign of the first derivative, second derivative. Usually, let me do one more example just from scratch. I just feel that we might need more. Okay, so this is a simple example. Okay, so it's a cubic polynomial. It will have some intersections, some x-intercept, and so 3x squared minus 3. Okay, so don't jump. You could compute the second derivative right away, so that you don't have to do differentiation again. 6x, the end. Okay. Okay. Then you'll need the signs of these. Okay, so the second derivative is easy because 6x. This one takes slightly more work, and that is why you need to factor it, which is uncomplicated. 3x minus 1x plus 1. Okay, it is a quadratic polynomial, so it's not hard to figure out its sign, where it's positive, it's negative. But you could just as well have a table for it, and so on the x-axis you mark the important points, and the important points are where v is equal to 0. And the important point that this one will be x equal plus or minus 1, and here x is equal to 0. Okay, so these are the important points. I marked them on my graph, so this is 0, -1, and 1, and they will be separating, just like with that picture we just had. They will be separating the different behaviors or different patterns. So I list my derivative first. So it will have x minus 1, x plus 1. Okay, so x minus 1, so up to, it remains negative up to 1, becomes 0, then becomes positive. Right, this one is still negative up to -1, becomes 0, becomes positive. Okay, so then the whole thing then becomes the derivative, that is. It becomes positive, negative, and positive again. Okay, so which means that my function behaves this way. And that's a general picture. Roughly speaking, that's what the function will look like, except this picture is questionable because it presumes concavity, and we don't know that about, and we don't know anything about it just yet. So we proceed to the next level and do the second derivative, which is very easy because it is simply 6x. So what do we know about 6x? It's negative up to 0 and then becomes positive. Okay, which means that we have for function f, we have concave down, concave up, and that pretty much confirms our picture, and we know where our inflection point is. It is right in the middle on the x-axis, on the x-axis as well as the y-axis. So this is what the graph looks like. Okay, so increasing up to 1. If you are plotting, please mark the points of importance. So these -1, 1, that's the minimum maximum points. these are the values of x. Naturally, frequently it's also a good idea not only know the points of maximum minimum but also the values. So you plug in back these values. So the important points right here, these three, find where they are located on the graph because it's important. So for example, f of -1 is -1 cubed minus 3 times -1, which is 2, right? And then f of 1 is 1 cubed minus 3, -2. Okay, makes sense. So then, like I said, this is 2 and this is -2. And certainly the other one, the last point is 0, so we know that this is the inflection point right here. Two maximum point, one maximum, two extreme points, and an inflection point, and we have the graph. Okay, so you might encounter more functions more complicated than that, but certainly not typically. It's more important to understand the ideas than to go through a lot of algebra. Okay, so any questions about this? Okay, so the byproduct. Well, let's kind of review what the first and second derivatives tells us about the extreme points. I think I want to start in here. Maybe next time. Okay, extreme points. So extreme points again. So so far what we have had was Fermat's theorem. And here I'm still mean local. And so C is a local extreme point. If then f prime of C is equal to 0 or undefined. That's pretty much it. So we cannot certainly anticipate differentiability, so it has to be checked. Okay, so it does not tell us vice versa. The fact that the derivative is equal to 0 does not mean that you have a minimum maximum point. Okay, so then that suggests a different look. How do we classify? That's the question. How do we classify the extreme points? And by the extreme, by classify, I mean it's not a large classification. It's either maximum or minimum. How can we tell which one it is? And the answer is actually the first answer. There will be two. It is the increasing decreasing behavior changes. So, okay, if we take this, by now it looks familiar. So this is a maximum. What is so special about it? Look at it. It starts decrease, then increase. I'm sorry, increase, then decrease. And then what happens? Of course, there is no other choice, but in the middle there will be a maximum point. That just you don't even need the picture. All you need those arrows. You go up and then you go down. What's happened right there? You have a maximum. So that's all there is. So then how do you describe it? Well, let's do the other one. And the other one tells us this is the minimum. And what's happening is the opposite. So it's first decreasing, then increasing. Once again, just looking at the arrows is sufficient to draw that same conclusion. Decreasing, then increasing, that's all. And that is the... how do we translate this? How do we translate this? Translate into the language of f prime, of the derivative. It's not complicated. I mean, increasing, first derivative is positive, decreasing, first derivative is negative, and so on. Okay, so all you have to do then to classify, to distinguish between the maximum and minimum, to see what happens to the derivative. Does it change the sign, and which way? Okay, which way it changes the sign. So this is called the first derivative test. So looking at the change of sign of the derivative. Okay, so suppose f is differentiable on an interval open interval I. Okay, and that contains a point, our point of interest. Okay, then there are two possibilities that are just illustrated right there. The one f prime changes its sign at x equals c. Well, let's put x here. So f of x, it is a function, so as you progress from left to right, the derivative changes, as every function would. And then which way does it change the sign? So it changes its sign from plus to minus, then, well, if, then x equals c is a local maximum. Okay? Just like that picture indicates, from plus to minus, that's what the first derivative does. And then secondly, if f prime changes its sign at x equals c, once again progressing from left to right, and then something is happening here from minus to plus, then x equals c is a local minimum. Okay, so that's the first derivative test. The way we have been doing it is we pretty much have been using it already, right? So because every time we draw these pictures, as you can see, we can see the change of sign. So over here is exactly what we just talked about. This is it. The first derivative plus plus plus, and then minus minus. So changes from plus to minus. What does it mean? It is a maximum. All you have to do is just to look at the arrows. First up, then down, then what's in the middle has got to be a maximum. And then it changes the sign from positive to negative. Then what's in between has got to be from negative to positive, so it's a minimum. The only danger is if you're not careful, you might run into a point where the function is undefined in the first place. Okay, as we've seen it over right here. The function is undefined, so there is a change of sign. No, actually there is no change of sign here, but you can imagine you just have to pay attention to the statement of the theorem, which requires the function to be differentiable on the whole interval that contains c, which means that it is differentiable at c, which means that it is defined at c, so there is no gap in the domain. If there is a gap in the domain, this is what can happen. You can have this. This is the gap in the domain, and look at what's happening to the derivative. Positive, negative, right? It changes the sign from positive to negative, and yet this is not a maximum. You see it? There is no point there. So also that function does not have a maximum to begin with. It's as simple as that. And in fact, it just doesn't fit into the definition, because the definition of maximum refers to intervals. So you can only speak of an interval of a maximum on an interval. Well, that's a global one, and the local one, once again, has got to be defined on the whole interval. Okay, so that is the first derivative test. Not to be confused, once again, can't help it but point out that the converse isn't true. So what am I talking about? The converse? It's about this part. If then, if it changes its sign from plus to minus, then it's local maximum. What's the converse of the statement?
Would be if f prime of x changes its sign from negative to positive, the x equals c is a local minimum. Is not true?
No. What is not true?
Is not true?
No, that's the negation.
It's saying that we have to have a value.
Let me just answer that. The negation means that what you're saying that is the theorem is untrue, which is okay, which is certainly a valid statement to explore, except it's proven, so it is true. But no, converse is not that. What is the converse? It is if then, if followed by the first statement, then followed by the second statement. So what do we do to get the converse? First statement, second statement. What do we do?
You just switch them.
Switch them. Okay, so let's read it. Somebody read it.
If x equals c is the local max, then f prime of x changes its sign. X
Right.
equals c.
Right. Okay, so that's the converse, and it's not true.
Because it doesn't have to be a maximum.
No. The maximum is given. The point is no. If it is a maximum, the change of sign does not have to happen. So this is the example that just illustrates it. What can happen is so even though it is a maximum, there is no change of sign in the sense that we have discussed. And the function is differentiable, so that still stays. Here's the weird behavior. Okay, so between two parabolas, we have a squeeze function that oscillates infinitely many times. Okay, so there is no doubt that this is a maximum point, right? Because everything else, the rest of the graph lies below the x-axis, so it's a maximum. But you can see that what's happening to the derivative, to the sign of the derivative.
It's going from positive to negative.
All the time. You cannot say that the sign has changed. It has been oscillating between plus or minus, and then it continues to oscillate between plus or minus. So there is no change of sign. Okay, so there are these weird examples are the mathematicians like to disprove things, because sometimes the theorems it's always, if you have a theorem, you want to think about, is there a converse, and frequently it is when there is, you have to prove it. Proving is hard, or maybe it's untrue. Then all you have to do is just supply one example that shows that the theorem is not true. So since we supplied one single example of a function that does not satisfy that hypothetical theorem that we just thought about, well, so there is no such theorem. And so it can go only one way. Okay, I have, see here, I have a large example. Let me go on to the second derivative test, which is much simpler, but uses the second derivative. Okay. You already know the answer, I suppose. So the second derivative test. And the test is once again to classification of extreme points, the separating max from min. That's all. I mean, if you think about it, you're doing an optimization problem, and the Fermat's theorem only gives you a bag of candidates, and you don't know which one's which. You need maximum, and then you have a bunch of minimums there in the bag too. So how do you classify and throw those out? Well, either with the first derivative test or the second derivative test. So suppose f is twice differentiable. On an interval, well, actually at x equals c at one point, so twice differentiable, and no, you just need the differentiability at one single point. So f is twice differential, so and the first derivative is equal to 0. Okay, so we have a critical point, and the tangent line is horizontal. The function is differentiable to begin with. Okay, then, so we once again have two cases, and that is simply, remember what the answer is. How do we use the second derivative to classify max and min? This is min, and this is max. What do you see about the second derivative?
Is it like the concavity of it?
Well, yeah, so the concavity is the sign of the second derivative. So when do we have a minimum?
Positive and negative.
Positive or negative second derivative at that one single point. We don't even have to look around, change of sign or anything. One single point of the second derivative. So if f double prime c is less than 0, then c is a local maximum. Right? So the slope is changing. So this is number 1. And number 2 is the opposite. If f double prime of c is larger than 0, then the slope is increasing, and c is a local minimum. Okay, so just as with the first derivative test, there is a gap there. Don't assume that all the possible outcomes are taken care of. And so we just saw that example with the first derivative test, that it is possible that neither condition 1 nor condition 2 is satisfied, and that's the example. So there is no change of sign. The function does not have to change its sign. Nothing says that it has to. Similarly, here what we have here is there's a still possibility, even though the function is twice differentiable. What's the third possibility?
It equals 0?
It is equal to 0. So the third possibility is f double prime is equal to 0. The test fails. That is a very harsh thing to say. The fails means that it literally means that the theorem tells us nothing. It doesn't say that it's that it's not a local maximum. It doesn't say that it's not a local minimum. It still could be. It just happens, and you can certainly think of a few examples when you have either. So second derivative equal to 0 or maximum, or minimum. It's not hard to think of. X to the fourth. Okay, x to the fourth. F of x is equal to x to the fourth. Okay. Looks almost like a parabola, except the kind of bottom is flatter. Okay, but if I differentiate, f prime of x is equal to 4x cubed, second derivative is 12x squared. Okay, so it is equal to 0 at x equals 0, and it is a minimum, as you can see. So it is possible. So all the examples are, you can have one way or the other, and you don't know. Okay, certainly you can think of a minimum. If I just put a negative sign over here, then I will have what? I'm going to have a maximum like this. Okay, so it's all possible, and that's why, in a way, the first derivative test is kind of more reliable in that sense. Okay, so let me do an example of. Let me do one more example, because I just have it here. Slightly more elaborate and complete analysis of a function, of a specific function given by a formula, and and it is a rational function, so it's slightly more advanced stuff as far as differentiation is concerned. So my function is x squared over x squared minus 1. It's not that complicated, but in the beginning. But you know, when you have a polynomial, you differentiate, it gets simpler. If you have a fraction, it does not get simpler. It frequently gets more complicated. Okay, so let's, well, first of all, let me, since I'm doing complete analysis, there is stage 0, stage 1, first derivative, stage 2, second derivative. Okay, that's roughly how you can think of it. But stage 0 is, what is it? XY intercepts and asymptotes. Okay, so let's look at the x-intercepts first. What are the x-intercepts? It's a good time to review this stuff from a while ago.
When y equals 0.
Right, and which is this. So take y equal to, the x-intercepts where y equal to 0, so x squared. It is pretty much, you end up with this equation, and you solve it. So what's the answer?
0.
Is that it?
If it's 0 on the bottom, then it's undefined.
Right, right. So common mistake to set denominator equal to 0 and also include those points. They are not. They are actually coming to the right in the next step, which is what is so important about x equal plus or minus 1. That's where the denominator is equal to 0, right? So what's so important about these 2 points?
Those are asymptotes.
Those are asymptotes, vertical asymptotes. Okay, so then that certainly already you can suggest what the graph might look like. It's like this, and then somehow the graph approaches these 2 vertical lines. So these are the asymptotes, vertical asymptotes, one and the other. Okay, but then remember we talked about that some time ago. The graph might approach this either this way or that way, and we don't know it yet. So either we look at a more careful way at this. So which way we don't know, or another way is to look later, postpone, and then deal and use concavity. Do you see the difference? This one versus that one.
F double prime is either positive or negative.
Right, so since we're going to do it anyway, we can just as well use the second derivative to distinguish between these 2 possibilities. So we postpone. There is one more step here.
Horizontal asymptote.
Horizontal asymptote. Okay, how do we find it?
Good question. Do we just divide the
You could, but
synthetic division or whatever?
you could, but that's not the sort of like like not the way to answer. That's how you compute it. What is that? The answer is always the same. Either vertical or horizontal asymptote. The answer is there's a limit. Remember, so that's how we started the whole thing, with a bunch of limits, and then I didn't write it limits here because we don't know which one it is, but if you look carefully, that you can certainly say about the vertical asymptotes based on that picture that as x approaches plus or minus 1, y goes to infinity. It's one or the other. Okay? With a horizontal asymptote, it's similar, except, well, it's not actually similar because you have to actually compute the limit of the function. X goes to plus or minus infinity, and then you apply that technique that you mentioned in order to compute it. So what is the technique? Either technique or whatever, there is a statement that makes it clear. So how do we compute this limit? Remember, x is very large, which means that some things are more important than others. What things?
The bottom is more important than the top.
No, they're equally important. It is that one is not important. That one is not important. The language is the leading terms are important.
Oh, so it equals 1.
So the answer is 1 then. So and that is the y, and y equal 1 is the horizontal asymptote. Okay, and now we're moving to stage 1, which is the derivative. So we find the derivative first. So f prime of x is the derivative of this fraction. So we got to use the quotient rule. Okay, quotient rule. The derivative of the quotient of a fraction is not equal to the fraction of the derivative first. Okay. So just I guess you have to make that mistake enough times in order to actually arrive to the conclusion that it is a typical situation when your intuition leads you in the wrong place sometimes. Okay, so let's differentiate. So how do I differentiate fractions?
2x.
I differentiate the numerator first, so it's 2x times
x squared minus
x squared minus 1 minus x squared, and once again 2x, right? The derivative of the denominator. Okay, so we got it. At this point, when you only ask to differentiate, especially on the test, you can just stop here, and that's fine. I can see how you have applied the quotient rule, and everything is okay. However, that's not going to be sufficient now because we got to do some algebra with the derivative. So we have to simplify. That's how algebra comes into play, and these skills that you may have brought from before will be very helpful. So we simplify. I have then what? I have 2x cubed minus 2x minus 2x cubed, x squared minus 1 squared. Okay, so 2x cubed disappears, and I'm left with negative 2x over x squared minus 1. I think I put a minus here just for convenience. Okay, so stage 1, so we're not jumping ahead to the second derivative, we're doing still the first. So factoring. Okay, so there's actually one more step to do, and that's the factoring. Fortunately, I could get 2 out of the way, negative x in the numerator, and I have to factor the denominator. I'm sorry, I left the square here. Well, actually, in retrospect, it actually doesn't matter. We don't have to factor it because why don't we have to factor the denominator?
Well, because we know it's plus or minus 1.
No, because it's never negative.
What is it?
The denominator. Well, let me write it out. So suppose these are the only fractions that we have, and I list them here, negative 2x and x squared minus 1 squared. Okay, negative 2x gets to 0 at 0. Okay, in the meantime, the x squared minus 1 squared is equal to 0 at negative 1 and 1. Empty hollow dots to indicate that it's undefined there. Okay, so now negative 2x starts positive and then becomes negative. In the middle it is 0. Okay, now x squared minus 1, what's happening to it? Well, first of all, I'm sorry, let me correct this. This whole should be probably emphasized. There is no place, let me put it this way, like a gap here, a stop. So plus, 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 gap, plus, 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 0, minus, minus, gap, minus, minus. Okay? Okay. So x squared minus 1 squared, what are the signs?
It's always going to be positive.
It will be always positive, except for 0 here. It might, well, yeah, but it's still undefined, so there is really no need for, there is not going to be happening here anything, ever. And then it remains positive all over positive, positive, positive. So now I divide or multiply. The rule still applies. Plus plus gives you plus. So that's my first derivative. Plus plus, plus plus, minus minus, minus minus. Okay. The function itself then will be once again separated. These separating points are very important because remember, monotonicity is defined on one interval at a time, and that's best we can do in these circumstances. Up, up. So it's not one up, okay, because there is a gap in the middle. I cannot say that the function is increasing on the whole interval from negative infinity to 0. No, there are two separate ones. Increasing, then increasing again. Similarly here, decreasing, then decreasing again. And at 0, we'll already identify a maximum point. Change of signs, right? Okay, so that certainly is already informative. You can actually refer back to the sketch that we tried to start, and we can already tell which one do we go to plus infinity or minus infinity. Look at the picture, and we're going to plus infinity. Okay, so we don't even need the second derivative. For some reason I brought up the second derivative, even though the first derivative is sufficient to distinguish between those two possibilities, increasing and decreasing. So we could just as well do that. So once again, this is my graph. These are my two asymptotes, negative 1 and 1. There is the second, the horizontal asymptote as well. Okay, And now we know that the function will be increasing towards, so over here it is increasing. You see it? You see my, can you see it here? I mean the pointer.
Yeah.
Okay, so it's here. We're talking about this area where the function is increasing, and it also has to approach the, well, let's start here. This is the only way to approach the vertical asymptote x equal -1, because we cannot go down. We are increasing. Okay, if we go to the left, hypothetically we might dip under the asymptotes and then approach it, but that, you see what happens. For that to happen, you'd have to decrease. So we discard that possibility, and this is the only way for anything to happen. Okay, a similar thing happened over here. Once again, it has to approach the vertical asymptote on one hand and the horizontal on the other hand. So, and once again, it cannot dip under the asymptote, otherwise it will have to increase at some point. And in the middle, it's kind of uncomplicated because it goes up and down, up and then down, and maximum in the middle. And we know the x-intercept, the only one, the x-intercept. Remember, so this is what it looks like. So so that is pretty much all we care about. The only missing parts are, just as it has been before, is that we assume concavity in these pictures, and we are. How do we know that it does not increase like this with all changing concavity all the time, the wiggling? Otherwise we know that increasing, decreasing, but it might be changing concavity as best we can tell. So the second derivative then. So I'm taking then my first derivative and differentiate one more time. Okay, so -2x over x squared minus 1 squared. So that's my first derivative. And I differentiate it one more time. So it will be starting with the numerator. Well, probably you can start and differentiate this thing separately. Okay, let's stop and do that. So what's the derivative?
2x squared minus 2.
No.
Oh, you gotta do the chain rule.
The chain rule, that's right. It is the composition. Once you see a bunch of parentheses, it's the chain rule. Okay, so then the function on the inside, that is my u, that intermediate variable. Okay, so, and then the function on the outside is u squared, and its derivative is 2u. Okay, in the meantime, the derivative of x squared minus 1 is 2x. Okay, and so the chain rule, what does it do to the derivative? So I want to use the chain rule to take this information and write the answer. So what do I do with the derivatives? According to the chain rule,
You leave what's in parentheses and then multiply it on the end.
I multiply the derivatives. If you want to remember the chain rule, remember you differentiate both and then multiply. That's all there. So then that's why I write it like this. Even though there is an extra step to be made, the one more substitution to actually have the answer. Since u is equal to x squared minus 1, I have 2x squared minus 1 times 2x. Okay, so that's how the chain rule works. But it's hardly hard. It's the challenge is to decompose first, and secondly, remember that you have to decompose. But it's not harder. The formula is actually shorter than the quotient rule or even the product rule. So all you have to do is to differentiate and multiply. Okay. So okay, that is going to be the answer. Now we combine that information with the quotient rule. Okay, so we start differentiating the numerator, which gives me -2, right? And then multiply by the whole thing here we just found. So it's times 2 x squared minus 1, 2x, and then what do? Hold on. No, sorry, I messed it up. Now let me just move it. f double prime of x is, okay, so we differentiate the numerator, which gives me -2 multiplied by the intact denominator, right? And now I subtract -2x intact numerator multiplied by the derivative of the denominator, which we just found. So I have here 2x squared minus 1, 2x squared denominator. Okay. So once again, the chain rule is visible here. The quotient rule applied is visible here. So if it's just a test, you can stop here. But we gotta do algebra with it. Remember, we need to figure out the sign of this thing. So fortunately, if we did everything correctly, things supposed to cancel out a lot. Okay, so let me try out. So it's gonna be, I'm gonna expand the term on left, which is -2x to the 4th minus 2x squared plus 1. And here what I have is 8x squared times x squared minus 1. Okay, x squared minus 1 to the 4th. Expanding one more time, -2x to the 4th minus plus 4x to the squared minus 2 plus 8x to the 4th minus 8x squared. Same denominator. Okay, so what do we cancel here? What do we cancel here? Well, apparently not a lot. Okay, so so the 4th power gives me 4x to the 4th. I'm sorry, 6x to the 4th. 6x to the 4th. Then I have -4x squared and minus 2. Okay, so that's the 4th power. 2x, 3x to the, x to the 4th minus 2x squared minus 1. Okay, so I'm wondering if you, I think we have just a couple minutes left. The problem is we need to factor this. There is a trick, if anybody knows how to factor some of the 4th degree polynomials. No? The trick here is to see that only the even powers appear, which means that it is actually a quadratic polynomial with respect to x squared. So if I replace u with x squared, let's say I'll have 3u squared minus 2u minus 1. And then I use the quadratic formula in order to find its roots and then factor. Okay, we'll do it next time. This is a little bit longer than I expect.